Hi, everybody. Welcome to this distinguished seminar for optimization and data. So today it's our pleasure to have Professor Tamara Broderick from MIT as our seminar speaker. Tamara is an associate professor of electrical engineering and computer science at MIT. She's also a member of the MIT Lab for Information and Decision Systems, the Statistics and Data Science Center, and Institute for Data Systems and Society. She has a long list of achievements, which we should all aspire to be similar. So she has received a Presidential Early Career Award for scientists and engineers this year. She's a IMS fellow. She's received the ONR Early Career Award, a NSF Career Award. You know, early career awards, you name it, Tamara has it. So it's a real pleasure for us to have her visit us this week. She's also graciously offered to spend a lot of time on campus for 2 days, talking to a lot of members of the UW community. So please join me in welcoming Tamara for her talk today.
Thanks so much for that extremely kind introduction. It's really great to be here. I've been having an amazing set of meetings so far. So today I'm going to be talking about a check that you can run on your data analysis, namely a check to see if there exists a super tiny fraction of data that if you drop it will change your substantive conclusions. I want to highlight the two folks who are really the leaders on this project, my former PhD student and postdoc, Ryan Giordano, who's now a professor at UC Berkeley, and our amazing economics collaborator, Rachel Meager, who is definitely the economics expert on the applications that I'll talk about today and who's a professor at the University of New South Wales. Okay, so at a super high level, the type of question we'd like to ask is, when can I trust decisions made from data? You know, there's so many super important applications these days, things in personal finance, in personalized medicine, in education. We really want to make sure that we're getting these applications right. And there are just more and more of them all the time. You know, as we get more data and better computation, we increasingly can have these data analyses drive life-changing decisions. And so at a high level, we'd really like to say, man, we should be running so many checks on these data analyses to make sure we can really trust the conclusions. There's no way that I'm going to be close to being exhaustive today. Rather, I'd like to suggest one check that I think could be useful among many. And that's going to be motivated by the following observation, that typically, when we're running a data analysis, we're in a situation where first we have some available data, we use it to reach a decision, and then the whole point is to apply that decision in the future. And so an example of this that's going to come up a bunch of times today is randomized controlled trials of microcredit. So microcredit represents these small loans to individuals in impoverished areas, and the hope is that it's going to help bring people out of poverty. And so what economists do is they run their randomized controlled trial at a particular place in a particular time. But the point isn't to learn about these people at this time. It's to learn, does microcredit help people, and can we apply it in the future in step 2 and actually help people then? And so going from step 1 to step 2 is what we might call generalization. And we might be worried about that generalization if it turned out I could drop an extremely tiny fraction of my data and totally change the substantive conclusion. So here's a concrete example in a very real-life study of microcredit that I'll show you very shortly. It was a randomized controlled trial with over 16,500 data points. We can drop one data point and flip the sign of the effect. That's the difference between microcredit helping people and hurting people. Hopefully we all have a lot of intuition, like, man, I'm not going to make a huge investment in microcredit if, in fact, it's robust, non-robust in this particular way. And the broader methodological question we're going to ask today is, could I find if such a tiny data subset exists that I could drop it and change my conclusions? It'll just turn out that it's absolutely prohibitively, combinatorially costly to check that directly. And so the reason that I'm speaking today is we're going to check out an approximation. We're going to see an approximation can be fast, it can be automatable, it can be accurate. And in particular, what we do in our paper, and what I'll try to give a little hint of today, is an empirical and theoretical analysis of how this sensitivity, or more specifically, the sensitivity approximation, behaves. Okay, so in the rest of the talk, I'm going to start By saying a little bit more detail, when do we care about dropping these data subsets? I'd say how we'd like to drop them if we had infinite computational power, and unfortunately, we do not. We'll talk about how we really can't do this with brute force. And so we're going to need an approximation. We'll talk about the approximation. We're going to see that tons of analyses are in fact robust, but many are not in the form of robustness that I'm talking about here. And you're probably familiar with many other forms of robustness. And I just want to emphasize that this is a different one. In this case, the non-robustness I'll be talking about isn't just a product of gross outliers. It's not something where you could have known you had it because of your large p-values. It's not something that's decided by heavy tails, and so on. We'll start to get an inkling, and this is a lot more of this is in the paper, that it's reflecting some notion of signal to noise in the data analysis. OK, so let's start by talking about when do we care about dropping these tiny data subsets. OK, well, a first point I want to make is that robustness is not a monolith. Usually when we talk about robustness or sensitivity, we're always using that terminology as shorthand. We mean robustness to some change, sensitivity to some change. If I had a data analysis that was robust to absolutely every change in the data or the analysis itself, that'd be a really useful data analysis. I could just return 0 all the time, but it wouldn't tell me anything about my data. And so, of course, the real question we want to ask is, what types of sensitivity are concerning to us, are problematic for our particular data analysis? And of course, that's got to vary by problem. And also, there are many types of sensitivity that should be concerning to us in any problem. Again, not going to be close to being exhaustive. Rather, the thing I'd like to convince you of on this slide is that here is a type of sensitivity that is often concerning. OK, and in order to do that, and also throughout this talk, we're going to look at economics. Why economics? One, it's got incredibly important applications that affect all of our day-to-day lives. Two, my goodness, is economics a reproducible field, which unfortunately is not the case for every field right now. And so it's just incredible that we can reproduce so many really major papers in economics. And three, we got to collaborate with the wonderful Rachel Meager. We just had this amazing economics expert that we were able to work with. OK, so let's think of one illustrative example about one I might care about finding. Is there a tiny data subset I could drop to change conclusions? So remember, economists run their randomized controlled trials. And so let's suppose we're looking at a randomized controlled trial of some economic intervention like microcredit. So economists will say, hey, these people are going to receive microcredit randomly. These people will not receive microcredit. And then literally what they'll do is they'll essentially take an empirical average of something like a business profit, like some outcome among this group, and something like the business profit among this group, and they'll compare them. And they'll say, if the business profit is higher among the people who received microcredit in some statistically significant way, we'll conclude that microcredit was helping people. But you could imagine, hey, what if it turned out 2 really rich people just really benefited from having the microcredit, and now their business profit was way higher. And now, as a result, the empirical average is way higher. This is a case where I might like to know, hey, do these 2 people exist? And if I remove them from my data set, do I get a totally different conclusion? And I would be interested in that because really I'm interested at the end of the day, does microcredit help a lot of people a substantive amount? OK, so why can't we just use standard tools? We've got all kinds of standard tools that are meant to tell us specifically about generalization. And they're still super useful, but it's worth noting that they make assumptions, and those assumptions aren't always exactly correct. For instance, a lot of standard tools assume that the samples that I have from the population I'm studying right now, or the group that I'm studying right now, for instance, my microcredit randomized controlled trial, are IID from the same distribution as the people I'll look at in the future. Well, that's definitely not the case. Here maybe we're running a randomized controlled trial in Mexico at a particular time. Later, maybe we want to look at the US or Philippines or something like that later on. It's not exactly the same distribution, but we hope things aren't too different from IID, at least not enough to change our conclusions in our analysis. And the question is basically, well, maybe we should check. So more realistic is that the policy population is different from the population we analyzed originally. Standard tools might assume our model is correct. We definitely know that's not the case. Certainly, there's no way that a simple model is capturing all of the rich interactions between people and their environment that are relevant for economics. Standard tools assume the output is what we want. That definitely wasn't true in the example I literally just gave. We don't care about the empirical average of business profit in either of these groups. We care that microcredit was helping a large amount of people, a substantive amount. Does that matter? Well, we'd like to check. Truly, in general, we're reporting a convenient proxy. Standard tools assume that if data is missing, it's missing at random. We definitely know that small data, fractions of data are missing not at random in economics and in general in the social sciences. Does that matter? We'd like to check. And so in all of these cases, we'd be concerned if we could drop a super tiny fraction of data and change our conclusions. And I want to emphasize super tiny fraction. If we get to the point where we're dropping a ton of data and changing our conclusions, well, yeah, I mean, eventually, if I could change my data enough, all my conclusions should change. Yes?
What does policy population different from analyzed population mean?
So policy population is here I'm thinking where I'd like to apply my conclusions in the future, and analyzed population is the population I'm looking at right now. So for instance, in my microcredit example, if I ran my randomized controlled trial in this particular village, that's the analyzed population, and policy population is even the same village, but 10 years down the road, where I apply it in the future. Okay, I also want to emphasize, well, I'm going to illustrate with economics examples and some real-life data sets in economics and data analyses in economics. These concerns are absolutely not specific to economics. No matter what I'm doing, it's often, or we can imagine that it could be the case that the data I analyze is not perfectly IID with where I'd like to apply my conclusions. Definitely, it's always the case that my model is wrong, classic aphorism. The output is generally not exactly what I want. I'm generally reporting a convenient proxy. I mean, in some sense, this is the amazing success of statistics and machine learning tools, is that they can be used so widely, so easily, but as a result, we're using proxies. Missingness in data is probably more of a social science phenomena than other areas of the sciences, but it can happen, and when it does happen, we might be concerned about missingness not at random. Finally, I want to emphasize, there are plenty of cases where this should not bother you, but you want to be upfront about it. So here's an example. Suppose I'm studying any kind of rare event. Like maybe I have 100,000 instances of crime in one city, but I'm studying a rare crime, like it only happened 3 times in this city. And then I have another 100,000 instances of crimes in another city, but it's rare, and so it only happens, this rare crime only happens 6 times out of those 100,000 total crime instances. In this case, I wouldn't want to ask, could I drop a super tiny fraction of my data and change conclusions? Because yeah, I could absolutely drop all of the rare crime that I'm interested in studying and change my conclusions. Conversely, I should probably be upfront that if I'm comparing these 2 cities, I effectively have 9 data points, 3 plus 6. I don't have 200,000, at least for many purposes. Okay, so hopefully at this point, you're motivated to think about, hey, does there exist a super tiny fraction of data that if I dropped it could change my substantive conclusions? And so let's start adding a little notation and being a little bit more precise about this. So we're going to say, we might worry if we could remove a very small fraction of data and change our conclusions. So alpha is going to be that fraction. So necessarily, it's between 0 and 1. But remember, we're only really concerned if it's very, very small. What does it mean to change my decision? Well, it depends on how I made my decision in the original analysis. So I'll just give you some examples of other people's decisions that they have made, but it doesn't have to be this. Sometimes people make a decision based on the sign of an effect, like is microcredit helping or is it microcredit hurting? Sometimes people make a decision based on the statistical significance of an effect. Sometimes people make a decision based on sign and statistical significance. They might be concerned if I could change to a significant result of the opposite sign. You don't have to make these decisions. You can make Bayesian decisions. You can make other types of decisions. These are just illustrative. But once I have a decision, I can ask for something like what we're going to call a maximum influence perturbation. So that is to say, hey, suppose that I was interested in the sign of an effect. So I'll take my effect, and I'll ask, can I change it so much that I change to the opposite sign? And can I do that by dropping alpha fraction or less of the data? So this will be the maximum influence perturbation, and we can ask, was it enough to change the decision? If it was enough to change the decision, we're probably interested in what were those data points. And so we'll call that the most influential set, the data that we had to drop, or that we did drop, to achieve the maximum influence perturbation. OK, so in some sense, there's a super easy way to compute these values. That is to say, I consider every very small data subset. I drop that subset, and I rerun my data analysis. So what could go wrong with this plan? Well, let's suppose, for instance, that I had 16,000 data points. This is actually smaller than the randomized controlled trial I mentioned before. Suppose I'm concerned if I could drop 0.1% of my data and change my analysis, super tiny fraction of my data. Well, using this brute force method, I'm going to take every subset of size 16, that's 0.001 fraction of my data. I'll drop it and rerun my analysis. Well, a data set of size 16,000 has about 10 to the 53 subsets of size 16. If you've run any data analysis in your life, you know that it's optimistic to say it takes 1 second. But suppose it only took 1 second to run, then this check would still take over 10 to the 46 years. I think there's a lot of things nowadays where we say, just use parallel computing and it'll really speed things up. In some sense, this is embarrassingly parallel, but definitely parallel computing won't save you. You could have all the compute of Amazon and Microsoft and every other company in the Seattle area, and you're still not going to be able to run this simple check for a simple economics experiment. OK, so we got to do some kind of approximation. And what I'd like to do now is I'd like to show you the approximation before we see what that approximation is, like show you it in action. OK, so let's look at Angelucci et al. 2015. So this truly is a real randomized controlled trial of microcredits, in fact, one of 7 very famous ones. Has over 16,000 households. You can think of the households as being small businesses for this purpose, so they're receiving the microcredit. I can't emphasize enough how cool all the economics papers that I'll be discussing today are. They have absolutely fantastic reproducibility and data sharing. I mean, just really a field that many of us could learn from. OK, so they look at a few different models. My understanding is the more complex ones basically yield the same results as the simple ones, so let's go with the simplest possible one. Just a super simple linear model. We should have a lot of intuition about this model. So little n is indexing the small businesses, or the households, from 1 to 16,560. There's a single covariate, xn. It's a microcredit indicator telling us whether this household received microcredit or not. We know that after the randomization. Yn, the response, is the business profit. So we observed that as part of the randomized controlled trial. And by we, I mean the actual social scientists who did this actual experiment. And then we have a couple parameters. So you can think of theta naught as being what would be the base business profit if microcredit did not exist. And theta 1 is the thing that's really interesting here to economists. It's the microcredit effect. If it's positive, microcredit is helping people. If it's negative, microcredit's hurting people. If it's 0, it's not doing anything. OK, so the original paper finds, using OLS, theta 1 hat of negative 4.55 US dollars purchasing power parity for every 2 weeks, and a standard error of 5.88. And that's to say, this is a negative result, but it's not statistically significant. Certainly, you would not invest in microcredit based on this result. OK, so we'd like to check how sensitive this is. And in particular, again, can we drop a super tiny fraction of data and change the conclusions? First of all, for our approximation, it's going to take just 2 seconds to run, not 10 to the 46 years, so we can check. Second, we find we can remove one household and change the sign from negative to positive, but you are probably thinking, hey, wait a second, that wouldn't change my decision. I still would not invest in microcredit if I had a positive result, but it wasn't statistically significant. And I think more relevant is that we can remove 15 data points and get a statistically significant result of the opposite sign. So here we now have a positive effect, and it's statistically significant. It's more than 2 standard errors above 0. I think another thing you should be thinking right now is, wait a second, you didn't tell me anything about this approximation, so why would I trust anything you're saying? And that's a great intuition. I think most importantly, we tell you the points to drop at the end. And so you can drop those points, actually rerun the regression. So you've only done 2 total regressions, not 10 to the 53 total regressions. And you can see what actually changed. Did you actually get a change in the decision? And so from that perspective, any non-robustness you find is fully conclusive. It could only be worse than what you rerun here. And in fact, we did do this rerun, and we do indeed find this sensitivity is real. And this one too, but this is the more interesting one. OK, so some other really natural intuition that you probably have at this point is you're like, hey, this wasn't statistically significant to begin with. Maybe I should have just paid attention to that. We're going to see later that we can start from a statistically significant result and make it non-significant. by dropping a small fraction of data in a real-life example. You might be thinking, hey, I've heard of other types of robustness. The problem here must be gross outliers, or heavy tails, or reporting means. And indeed, that's super relevant and decisive for some types of robustness. But in this case, we're going to see these are not decisive. You might be thinking, hey, the problem is you weren't being Bayesian. If only you were being Bayesian. We're going to see that's not decisive. You can totally be non-robust while being Bayesian. Hopefully, we'll get a little bit of an inkling that the issue here is a signal-to-noise ratio in the data analysis problem. OK. So at this point, we talked about why do we care about dropping these tiny data subsets, saying, can we drop a tiny data subset and change our conclusions? Talked about how we'd like to do it if we had infinite computational power. We realized we do not. Even for moderately sized problems, we don't have enough. And so we need an approximation. And now what I'd like to do is just walk through the approximation. OK. So first, let's just write out a super generic data analysis. So we're going to have some data. We're going to index our data by little n. It'll go from 1 to capital N, the number of data points. We could be doing supervised learning. So maybe we have a set of covariates and a response. But we don't have to be. It could be semi-supervised. It could be unsupervised. It's just a bunch of data. We have some parameter, some unknown. Let's call it theta. It could be a set of parameters. It doesn't have to be one-dimensional. It could be very high-dimensional. We have some loss that relates our parameter to our data. Very typical thing to get a parameter estimate is we'll sum up over some capital N losses, each corresponding to our data points. Maybe we'll have some regularizer or penalty. Could be 0, too. That's totally fine. And maybe we estimate our theta by taking the minimizer over this sum of losses, this penalized sum of losses. OK, tons of stuff fits into this setup. We could do maximum likelihood estimation. We could do sort of just about any loss minimization. We're doing maximum a posteriori estimation. If we're being mildly Bayesian, if we're being very Bayesian, we can do variational Bayes within this framework. Actually, our methodology works more generally. It works for any z estimator. So we could have a series of optimizations. But I think this is much more familiar, this setup. And so I'm just going to write out this hopefully more familiar setup. OK, so we saw in the microcredit example just a moment ago that our analysis doesn't end there. So we do our parameter estimation, but then we actually make a decision with that parameter estimation. We don't just stop. We have the parameters. So we use a quantity of interest to make that decision. So for instance, if we were making a decision based on the sign of the microcredit effect, P, the index of the parameter, would have been 1 before. And we would have been looking at theta hat 1. If we were making a decision based on statistical significance or sign and significance, we'll use an endpoint of a confidence interval. So we'll have our estimator for a particular parameter plus or minus 2 standard errors. We could also make decisions based on a lot of other stuff, like posterior means and posterior credible intervals. Again, it's all going to fall under this umbrella. OK, so we have our quantity of interest. We're making our decision. Everything above this bullet point is hopefully super familiar from some introductory statistics or machine learning class. Everything below this is going to be standard things, but might not have been standard in a class. So the next thing we're going to do is we're going to give each data point a weight. So data point 1 gets weight W1, data point 2 gets weight W2, up to data point capital N gets weight Wn. We're going to collect all of these weights in a vector. Let's just call it W with no subscript. And in this original formulation, in the original data we get, all the weights are size 1. And so we can collect that in the all ones vector, 1 sub capital N. And a way that we can conceptualize dropping data is we can consider the corresponding weight going from 1 to 0. So if I drop the 10th data point, I take its weight from 1 to 0. If I drop the 10th and the 11th data point, I take both of their weights from 1 to 0. And so hopefully you agree with me that every drop data subset corresponds in a one-to-one manner with a different weight vector W. OK, so how does that change our analysis up top? Well, what we're going to do is we're going to take each of our losses, and we're going to pre-multiply them by Wn. So that is to say, if I include the data point, its loss is still in the objective. And if I remove the data point, its loss is no longer in the objective. And so that makes sense. This corresponds to dropping the data point. OK, so now theta hat is a function of w. As a result, phi is a function of w. It could be a function of w just because theta hat is a function of w. It could also be a function of w in other ways. For instance, the standard error has dependence on w, not just via theta hat. I say, so now we have this observation that phi, all of these 10 to the 53 different phi that we want to compute, are functions of w. But we don't want to compute it 10 to the 53 different times. That's a problem. So we'd like to approximate this. And our question becomes, how could we avoid all of these computations? Well, an observation here is we're only ever interested in changing w an extremely small amount. Remember, we said we only care about the cases where we're dropping a super tiny fraction, alpha, of our data points. And so we might think, hey, we're dropping a super tiny fraction. W is only changing a little bit. Maybe we could get away with a Taylor expansion as an approximation. Also, I feel like sometimes that's the only approximation that really exists at the end of the day. So how about we try Taylor expansion? Well, what are our options? We're not going to do 0th order. That's not doing anything. Second order is far too much. Let's just see if we can get away with a first order Taylor expansion. And that's what we're going to do. OK, so here I'm just repeating from the previous slide my generic looking data analysis with some weights in it, my quantity of interest, and now this super simple idea, just a first order Taylor series expansion. And in particular, what is it around? Around the original data analysis. W is equal to the all ones vector. OK, so let's just walk through this together. We wish we could compute the exact outcome of our data analysis 10 to the 53 different times. We can't. That's way too expensive. So instead, we're going to compute a linear approximation, by which I mean a first order Taylor series expansion. What is that? Well, it's the 0th order term around w equals 1. Phi of the all ones vector is what we get by just running the original data analysis. This is like a sunk cost. You had to run the original data analysis, and that's what we're going to get. Now, the first order term is basically going to be the w vector minus the all ones vector dot producted with the first derivatives. So these are just defined to be the first derivatives of phi with respect to w. If you're familiar with influence scores and influence functions, this is just the influence score of the nth data point. If you're not, don't worry about it. It's still just a first order Taylor series expansion. There's nothing really crazy going on here. OK, so let's make some observations. The first one is, how do we actually compute this derivative? That's something we're going to need to do in practice. Luckily, like so many things in life, people in the 60s and 80s did all the work for us. And so if you go back to work from the 60s and 80s, like Hampel, earlier researchers showed that we can turn this derivative of phi with respect to w via implicit function and chain rule into things like derivative of f with respect to theta and r with respect to theta. Now, back in the day, people were still like, man, that seems like a lot of work. I still have to get that derivative. What a pain in the butt. Thankfully, nowadays, we have modern automatic differentiation software, so we don't even have to worry about that derivative. We can fully automate that derivative. And so with these powers combined, this is just a fully automatable operation. I do want to emphasize the difference between automatic differentiation and numerical differentiation and symbolic differentiation. If you're not already familiar, there's this amazing overview by Baden et al. In 2018 that I think is really awesome read. OK, so the important point here is that we can compute this, but I'm not going to write down exactly the formula. The important point is the user doesn't have to do any of that work. They just give us their loss, their regularizer, and their data, and then everything can be automated. Implicitly in everything I just said is it has to be differentiable. So f has to be differentiable with respect to theta. R has to be differentiable with respect to theta. So it does limit you from things like L1. OK, 2, tons of authors have approximated or suggested removing some data points using the influence function. This is not even remotely close to exhaustive. I could probably fill up pages of authors doing this. Even back in the 70s, people were looking at approximating removing data points as a debiasing method for an estimator. More recently, people in the machine learning literature have looked at understanding the importance of data points in black box estimators using an influence function. We've done some work, along with many others, in approximating cross-validation using influence functions. You can think of that as being a form of dropping data, where you're saying, hey, if I'm doing k-fold cross-validation, I'm removing 1 over k of my data points at each time. What's different here is this notion of removing a fraction of data, a worst-case fraction of data. And so here we're not saying we have a particular set of data we're removing. We're interested in this maximum influence perturbation. And to the best of our knowledge, nobody had empirically or theoretically analyzed that yet. I'll also note this can be seen as a special case of a breakdown point or local robustness, although I think usually breakdown point is more conceived of as changing the actual data values in some intense way. But in a very general sense, this can be seen as a special case. Local robustness, we really came from this literature, where people are interested in things like if I change my likelihood, if I change my prior a little bit, how much that would change my outcome. And so we're really indebted to that work. OK, but we're not done yet. And to see why, let's first consider this question. First order Taylor series expansion, I've heard of higher order Taylor series expansion. Why have we stopped there? And the answer is, this could be cool, and this could be useful for other things. It might be important if we're trying to approximate something like a bootstrap. But in our case, we're not done yet. There's still too much computation, and it'll be pretty important that we're actually using a first order Taylor series expansion when we actually really think about computation. OK, why is there still too much computation, by the way? Well, we said we didn't want 10 to the 53 exact computations. But I'll tell you right now, you don't want 10 to the 53 linear approximations. You don't want to do 10 to the 53 additions. That's still like way too many additions. And so that's what we got to get rid of. We got to get rid of these 10 to the 53 operations. OK, so again, just copying things from the previous slide. The observation that we're going to make in order to try to get rid of this too much computation that still exists is at the end of the day, what we care about is, can we change our conclusion? And so remember, we have this quantity of interest, and we're interested in changing it in a particular direction. Like if I have a positive quantity of interest, and I care about the sign for making my decision, I care about, can I change the quantity of interest? Can I change the effect so much that it changes the sign? And so I'm going to ask, how big can 5w minus 5 the all ones vector be? If I cared about the other direction, I could just use negative my quantity of interest, negative phi. So without loss of generality, let's consider making the change as big as possible in this direction. Well, using our approximation, we're not putting in 5w, we're putting in the linear approximation. Now this difference we can write using the equation, just two equations above there. All we've done is we've taken 5 the all one vector to one side. And we're left with just the first order term in the Taylor series expansion. And this just has really two options. Either wn is equal to 0, we're dropping that data point, in which case we get a negative influence score. Or wn is equal to 1, in which case this part just cancels out and it's 0. So now we just have the sum of the negative influence scores over the data we dropped, and this suggests an algorithm. The algorithm is the following. 1, compute the influence scores, these things. It's going to be a linear time operation in the number of data points, because you just compute this one time for each data point. 2, sort the influence scores. Technically speaking, you only even need the top alpha, but let's just say you have a sort. That's n log n. 3, remove the most negative influence score. So if I'm interested in the biggest approximate change I can get from removing one data point, well, I want to remove the score where this is most negative, so this is most positive. If I want to get the biggest approximate change from removing 2 data points, I want to remove the cases where the 2 influence scores have the most negative value, so this thing is the most positive it can be, and so on. And so before we were interested in this maximum influence perturbation, the largest change we can get in a particular direction, the one that would change our decision, by dropping at most 100 alpha% of the data. And so now I've just described how to get the approximate maximum influence perturbation, to estimate the biggest change we can get by dropping at most 100 alpha% of the data. And along the way, we can ask, which data points did we drop, just which indices were those? And that'll be our approximate most influential set. The data dropped to achieve the approximate maximum influence perturbation. Now, this is exactly the approximation that we saw on the previous slide when we were looking, or a previous slide, We were looking at the results of that microcredit analysis. And now what we're going to do is we're going to spend some time together developing some more intuition for what this is doing. OK. So first, I'm going to start with a synthetic example, because that's one where we can completely control everything, and we have tons of intuition. And then I'm going to go to some real-life examples. OK, so here, we're going to simulate data from a linear model with Gaussian noise. We want something that's an extremely simple model we have tons of intuition about. And we want it to be simulated so it's perfectly specified. We don't even have issues of misspecification. So we'll just have our linear model. We'll have a single covariate xn, a single response yn. We're simulating things. So we're going to simulate data with noise that's IID with some variance. Let's call it sigma squared epsilon. We're simulating everything, so we've got to choose our covariates. Let's just choose our covariates in this somewhat unrealistic way, but useful for illustration, where they're all IID, and they've got their own variance, sigma squared x. And we're simulating everything, so we're just going to choose theta, and we're going to choose it to be 0.5. OK, so we have to say what's our decision here. Let's just suppose for the moment, for illustration, that we're making a decision based on the sign of theta hat. So we're going to fit theta hat with OLS. We're going to have 5,000 data points that we fit OLS to. And then we're going to ask, can we flip the sign of theta hat? Now, I said earlier that there was going to be a signal-to-noise ratio implicated in the problem. Now, there's a very general notion of what that means, but let me say what it means in this specific case. So signal, very generally, not just in the specific case, is going to be the size of change of interest. So in this specific case, I fit my OLS, I get theta hat, and I'm asking, can I change the sign of theta hat? To change the sign of theta hat, I have to go to theta, from theta hat to 0. That's what it would take, for instance, if theta hat was positive, I would go down to 0, and that would get me to a negative theta hat. And so the size of change I have to make to change the sign is the absolute value of theta hat in this particular case. The noise, very generally, is an estimate of the scaled asymptotic standard deviation of the quantity of interest. In this particular case, it takes a really nice form. It's approximately equal to sigma epsilon over sigma x. Let's think about our intuition here. So signal is making this an easier problem. Noise is making this a harder problem. If sigma epsilon is very small, and sigma x is very large, so here sigma x has quite a range, and sigma epsilon is very small, this is a case where you could drop a tiny fraction of data, and there's just no question about what sign this is. I think if anybody in this room disagreed on the sign of this effect, we would all look at them and say, you're obviously lying. I think we're all absolutely confident of what the sign of the effect is in this regression. Conversely, suppose we had the exact same theta, but our sigma x was super duper small, and our sigma epsilon was super duper large. This is a case where I think we can't reasonably eyeball what the effect size is, and it's super vulnerable to dropping a small fraction of data. I could drop a little bit of the corners, and I can get a negative effect. I can drop a little bit of these corners, and I can get a positive effect. And so what we're going to see is that the signal-to-noise ratio in this problem really tracks the robustness to dropping a super tiny fraction of data. OK, so let's see that in actual experiments. So what we're going to do here is we're going to change sigma epsilon on the horizontal axis. You notice it's a logarithmically increasing scale. We're going to change sigma x on the vertical axis. And so in this corner, we have a very high noise and a very low signal-to-noise ratio. In this upper corner, we have a very low noise and a very high signal-to-noise ratio. Now, these little colors you see are us plotting, using our approximation, how much data do we have to drop to change conclusions. And here in this corner, where noise is very, very high, we see that we can drop a very small fraction of data and change conclusions, like 0.2%. As noise decreases and signal-to-noise increases, we find that we have to drop more data to change our conclusions. Eventually, we have to drop 1% of the data and change our conclusions. Eventually, we have to drop more than 1% of the data and change our conclusions. Eventually, we have to drop so much data that, remember, we're actually doing a first-order Taylor expansion, and you shouldn't really trust it when W is getting very far from the place that you were running it. And so these black X's indicate this approximation, this first-order Taylor series approximation is dubious. You shouldn't be trusting it anymore. And eventually, we get to the point that gray, where we can't even find data to drop to change our conclusions in the approximation. It probably still exists in real life, just not in the approximation. OK, but this region we don't care about, because it's a region where we have to drop a ton of data. The key observations are, 1, we can detect if there exists a super tiny fraction of data that if we dropped it would change our substantive conclusions. If it's small, we can say how small. If it's large, we can't say how large, but that wasn't the point anyway. We didn't care about that. We cared about when it was very small. OK, a few other observations. So here we're seeing that the sensitivity, the type of sensitivity I'm talking about today, to dropping a super small fraction of data, tracks the signal-to-noise ratio, at least in this particular problem. And we're also seeing a number of things that are not decisive. So this isn't just detecting misspecification. These are perfectly well-specified problems where we can have both sensitivity and lack of sensitivity. This isn't a problem where means or heavy tails are decisive. Everything here has light tails, and still we're seeing both robustness and non-robustness. Everything here is computing essentially a mean, and we're still seeing both robustness and non-robustness. This isn't just detecting gross outliers. Arguably, there are no gross outliers in these examples. OK, so next, let's look at a bunch of real data analyses. These are all awesomely reproducible. Again, I can't say enough nice things about the economics field. Very cool. First, let's see that it's not just non-significant. So remember earlier we had an example where we could go from non-significant to significant. Let's see the other direction. Your neighbors in Oregon had a thing where the winners of a lottery could sign up for health care. It's a real thing that totally happened in the United States. So a number of economists recognize this as being a natural experiment, that they might look at, hey, do the winners of this lottery have better health outcomes? And they had over 21,000 data points, which in this case were surveys. So they had to look at survey responders. So missing data is definitely an issue. Arguably, it's much more than a small amount of missing data. I can't emphasize enough how much this is a tough problem. Even quantifying what health means in a way that's actually measurable is really tough. We probably want health to mean something in a very long-term sense or in a very carefully measured sense. And the reality is we have the data that's available to us. So this particular paper looked at a lot of different notions of health. One notion of health among many is the number of days of good health in the past 30 days, about a year after the original randomization, the original lottery. There are a number of other ones. Our paper reproduces all of them and also looks at sensitivity. I'm just going to talk about this one right now. The original paper and also our paper's reproduction looks at both the effect of the lottery win and actually going through and signing up for Medicaid on health outcomes. So here I'm just looking at the lottery win. So one of the results was p less than 0.01 for a positive effect of lottery win on this very particular measure of health. And we find that we can drop 10 data points and change the statistical significance there. Now, I want to emphasize this is not 5% of the data. It's not 0.5% of the data. It's really 0.05% of the data, so a super, super tiny fraction of data, where we're able to go from a statistically significant result to a non-significant one. OK, 2, I think another intuition we might have is, hey, maybe if I was just Bayesian, or I used a more complex model, maybe the problem is linear models. If I used a more complex model, I wouldn't have this problem. And these are not panaceas either. So our collaborator, Rachel Meager, actually is arguably both an expert in economics and econometrics, as well as Bayesian inference. Rachel did the thing that I think seems very natural here, if one's a Bayesian, which is to say, hey, we've got these 7 randomized controlled trials. Why not share power across them? Why not have a hierarchical model and then ask, what's the global effect of microcredit using that hierarchical model? Rachel, having experience in Bayesian inference and also econometrics, carefully chose likelihoods and priors. These weren't just sort of the default squared error Gaussians that I've talked about so far in this talk. But it's still all sensitive. So we still find that even with all these careful choices and Bayesian analysis, that it's still a sensitive analysis. We can drop less than 0.03% of the data to change a sort of Bayesian notion of statistical significance. So in particular, if 0 is in the 95% credible interval for the microcredit effect across countries. And we can drop less than 0.1% of the data to change the sign of the effect. Again, I want to emphasize it's not somehow about care in the analysis. Sometimes an analysis can just be a sensitive analysis. That's not any disparagement on the researcher. Okay. You might also be thinking, man, maybe just everything's non-robust. That's not the case either. Technically speaking, we already saw that that's not the case in the simulations, but you might be thinking, well, maybe everything in real life is non-robust, but that's not true. So we looked at this other cool study, effective cash transfers on consumption in poor households. This is by Angelucci and DeGiorgi, 2009. So slightly different setup. Now it's cash transfers instead of microcredit and consumption instead of business profit. They had over 10,000 data points. And we find you have to drop a ton of data to change the conclusions. We looked at trying to change the sign. We looked at trying to change the significance. We looked at trying to change to significant approximate or to a significant result of the opposite sign. And we got to drop like 4% or 10% or so much that we're not even sure about the Taylor series expansion approximation anymore. I wouldn't even trust that this is a number. I would just trust that it's a large number. Okay, another thing that we might have thought is that this is just equivalent to outlier detection. Maybe if we removed outliers in advance, that would be some kind of panacea. Arguably, we should probably check our outliers in general and not just remove them. But let's consider a case where that did happen. So Angelucci and DeGiorgi, 2009, same paper, had another really cool aspect of the paper. So it's this idea of, OK, so these poor households in the village are receiving microcredit. But you could ask, did the non-poor households that were in the same village, did they benefit from the poor households receiving microcredit? And so they ask about the spillover effect with non-poor households. And the original analysis removes the largest responses. So some kind of outlier trimming, something you would expect from certain types of classical robustness amelioration. But we find even after that removal, we can drop 3 data points out of 4,000, over 4,000, and change the significance. So it's not about just outliers. We really can have other types of non-robustness as well. That's not to say that all these things don't possibly contribute to non-robustness, but they're not decisive. OK. So I'll talk really briefly about some more general theory we have in the paper. And I think, in some sense, the reason that we want theory is we want to check, did we just get lucky or unlucky, depending on your perspective, in those special cases? Maybe they're not really illustrative of a more general case. And in particular, 2 of the things that we're really interested in are, one, is the approximation sufficiently accurate to use? I mean, one nice thing is we know that if you drop these data points, it's truly decisive. But there could be more non-robustness. So that's why we care about approximation accuracy, is could there have been more non-robustness than the particular data set we flagged? And then 2, I mentioned the signal-to-noise ratio interpretation. And so we want to dig into whether that's a more general thing as well. OK, so first let's look at accuracy. Somehow what we'd like to say is that the linear approximation is close to running the full data analysis for each dropped data subset. An immediate tough question is, what does it mean to be close? We don't really have a scale. And so here is one potential scale, is we'd like the linear approximation to be closer to actually dropping the data than actually dropping the data is to not having dropped the data at all. Certainly, we'd be kind of sad if this was bigger than this. OK, but it's not just that we want this to be closer than this. We really want sort of the worst case to be closer. Because remember, we're doing this kind of worst case analysis over all these dropped tiny data subsets. And so let's call capital W alpha the collection of W's where we drop at most alpha fraction of the data. And so we want the worst case difference here to be small relative to this. OK, I'm going to do this annoying thing that happens sometimes in theory, where I'm going to compare bounds instead of comparing the actual values. We have reason to believe that these are tight in some cases, but these are still upper bounds. So here we have a constant times alpha. So alpha, remember, is a small fraction we're dropping. And we're going to consider alpha going to 0. That'll be the asymptotics we consider. And you might be thinking, I think when I look at this, I'm thinking, wait, isn't this backwards? If I want this to be smaller, shouldn't this be square root of alpha and this be alpha? But remember, we're taking alpha to 0. And so alpha is actually smaller than square root of alpha in that regime. OK, so the observation here is under smoothness and regularity conditions, the bounds on the error in the linear approximation shrink faster than the bound on the difference due to dropping data as alpha goes to 0. I can't emphasize enough that this is a nice check. But this is still a first-order Taylor series expansion. And you have a lot of intuition about a first-order Taylor series expansion. It's still going to fail when a first-order Taylor series expansion fails. Like many types of theory, the smoothness and regularity conditions are doing a lot of the work here. OK. 2, let's consider interpretation. So remember, we wanted to say we're interested in whether the linear approximation, the worst case linear approximation, the worst case drop data subset over the just small dropping data subsets, this W alpha, is sufficiently different from the original analysis that it changes our conclusion. So the way we can write that is that this is greater than some value, which we're calling the signal. So remember, just like before, the signal is the size of the change that would reverse our conclusion. Now, the observation that we make in our paper is that this difference can also be decomposed into what we might call a noise term and a shape term. The noise term is a consistent estimator of the standard deviation of the limiting distribution of the quantity of interest. That's the phi that we've been seeing this whole time, or sorry, the psi. The shape is just a thing that converges in probability to a non-zero constant. And so what does this have to do with anything I've said? Well, you can think of this as a signal, and this is a noise. So if we bring noise over to the other side, we have a signal-to-noise ratio. And we're comparing it to something that's at least converging in probability, in this case as n goes to infinity, to a non-zero constant. So we're doing a comparison of a signal-to-noise ratio to roughly a constant. Why is this useful? Well, I think one particularly nice observation is that as n, the number of data points, goes to infinity, this notion of sensitivity does not have to vanish. Oh, is there a hand? Thank you.
Can you say something about what shape represents?
About what? Oh, shape represents. I mean, roughly, it truly is representing the shape of the distribution, like the tails. The distribution here. OK, so something that actually I am putting under the rug here is that starting in this part, we're assuming that the data is IID from a distribution now. So just for the purposes of theory, I want to emphasize the difference between you do not need that to run the method. And if anything, I think we're really motivated by not making that assumption to run the method. But then in the theory, we're going to try this out. And so in that distribution that the data is truly being generated from, the shape is describing something about that distribution. Thanks. OK, so the observation here is that as n goes to infinity, the sensitivity doesn't have to vanish. And I think that's really helpful, because if you compare it to something like a p-value or standard error, if I'm in a situation with misspecification, aka always, then it's going to be that, well, first of all, just always period. As n goes to infinity, my standard error vanishes. And so if I'm in a case with misspecification, I can expect that eventually my p-value is going to get arbitrarily small just because I have a lot of data. And so here we're not seeing that behavior. We're seeing that we don't have to vanish just because we have a lot of data. It also follows as a corollary that statistical non-significance becomes AMIP non-robust as n goes to infinity. OK. So today I talked about a way to check if there exists a super tiny fraction of data that if you dropped it, it would change your substantive conclusions, whatever those are from your data analysis. And I talked a bit about an empirical and theoretical analysis of its properties, but you can read a ton more in this paper. Again, I really want to emphasize the amazing work of Ryan Giordano and Rachel Meager. This is only alphabetical because Rachel said that was the thing to do in economics. And so that's just why it is that way when you look it up. But really, Ryan and Rachel did amazing work here. You can find the code on Ryan's GitHub. So R Giordano is Ryan Giordano. ZAM influence stands for Z estimator maximum influence, sort of the thing we've talked about today. Now let me make a couple of hopefully final remarks here. So one is somebody who is totally not us and not affiliated with us in any way. This cool guy, Michael, made the observation that p-hacking is not robust in the way that I described today. Now I want to be super clear. I'm not saying if you find non-robustness in the way I described today, that means there was p-hacking. That's definitely not true. If you have p-hacking, you can expect it to be non-robust in the way that I described today. And Ryan, on his blog or website, describes in a bit more detail why you can expect this to be the case. It's really related to the asymptotics I just talked about, where sensitivity doesn't vanish as n goes to infinity. Of course, this is not specific to economics. If anything, we focused on economics because it's so reproducible to start, but we've also looked at differential expression analysis and genomics, and you can do this for a lot of other analyses. Today I talked about essentially optimization-based analyses, but we can look at other types of estimators. So we've started to look at things like Markov-Chain-Monte Carlo-based estimators, which come up a lot in Bayesian inference. I can't emphasize enough that there is so much work to be done on better approximations. Again, yes, we can rerun the analysis once with the drop data, and that's conclusive if we find non-robustness. But we have a lot of reason to believe that there are a lot of cases where we're not finding non-robustness that really exists. And so there's been this amazing follow-up work since our original work by Kushnik et al., by Ankar Moitra and Rahaki, by Freund and Hopkins, and by others. And we've also done some work sort of evaluating these methods, showing that there really is room for improvement. Essentially, we're looking at a relaxation of an optimization problem, but it's not the only one you could look at. There are absolutely better ways you could do this optimization, and I'm sure that people can come up with better things than what I've talked about today. I think this is just the start. I mean, arguably, there have already been a lot of interesting pieces of work. A lot of them, interestingly, have focused specifically on linear regression. The stuff I talked about today, again, was for general Z estimators. So again, there's quite a lot of room there. And finally, I just want to super emphasize this is not some kind of gotcha for economics as a discipline. We really needed reproducibility as a prerequisite to even run this. I happen to be on a paper, but really Ben Keynes did like amazing work, and all the work on this nature matters arising, or sort of a note, pointing out that there was this work released by Google on AI for healthcare, and there's sort of not even enough information to possibly reproduce the code, much less code that's released. And this is something we've seen a lot more recently. So this came up recently with a newer version of AlphaFold, where they didn't originally release the code, and there was this big back and forth, and then they released some things. But that was meant to be a prerequisite for publication in Nature, and certainly a big thing where there are really important applications right now where code isn't being released, where analyses aren't reproducible. So arguably, it's amazing that economics is so reproducible that we could run these checks and really just get back exactly the results that the original authors did. And in some sense, that's the reason we're looking in these directions. We can only assume everything else is going to have just as many problems when we look at it. And finally, again, I want to emphasize this is not like the end-all, be-all of robustness. I don't think anything is. I think it's one check among many we should run in our data analyses, and we talk about sort of an ecosystem of checks in the Science Advances paper, and many other people have talked about ecosystems of checks as well. And I just encourage you to be thinking about that when you're thinking about your own data analyses. Thank you so much.
Thank you, Tamara. That was awesome talk. We have time for a couple questions. Go ahead.
Hello. Amazing talk. Thank you so much. I'm wondering, so you had this example at the beginning where you removed 15 points to change a non-significant result to a significant result. Yeah. If instead you're starting from the data set that has, like, maybe 15 points are missing, is there anything you can say about that data set to sort of know about the robustness for, like, potential adversarial missing?
Yeah, I feel like this question really relates to another question that I sometimes get, which is sort of like, what if I were trying to gather more data? Like, where would I put it? Or how do I know, what else is needed or what's missing? And I feel like fundamentally, it's not obvious to me how we would answer that question, and it feels like a much harder question. Because I feel like the big thing that we're taking advantage of is that we can downweight existing data points, and sort of like the notion of upweighting a data point that we don't have access to feels fundamentally harder. So in some sense, I'm like getting around this by saying, man, if I'm still sensitive to a small fraction of data, then I should be worried that I could have lost some originally, and that could have changed it like in that sense, but it's not directly answering the question, as I think you're pointing out, that I can't say, oh, if you had like, if you were missing exactly these 15, that this could have really changed it. We're more just saying, hey, if it's sensitive, you should be worried that you could have been missing 15 that could have changed it. In either case, I would say, like if we think about what's going on, for instance, with microcredit, if it really turns out like, hey, this small fraction was hinging on things, you can say, I should worry about this a little bit. Maybe I should, or at least I should think more carefully about the study. I mean, we're not saying like, oh, there's this one thing you should do if you find this, but you should probably go back, look over the data, think about where it came from, think about what's going on there, just really carefully. You could also think of this as being somewhat asymmetrical, like hypothesis testing. Like we can say like, oh, we found non-robustness, we can't guarantee robustness. Thanks.
Yeah, great talk, thanks. I had a question about how this pertains to the bootstrap, which you brought up a little bit earlier, just because if we think about that as sort of dropping some points at random, which would be kind of a naive approach to here instead of enumerating all possible aspects. That seems very similar to the bootstrap, but there we don't really care about like the worst case of all those outcomes we observe. We care about kind of just the distribution, and are we kind of somewhere?
Yeah, we have a paper on the archive. It's just on the archive. It's not like a full paper. Only because we never got around to publishing it. But basically saying you can do a very similar type of approximation and you can prove theory about it. And so in the following sense, so two things that are a little bit different there. Now the weights are not just 0 or 1. They could be any integer up to n, technically, because of the nature of the bootstrap and how you're reassigning weights and data analyses. And then 2, the weights are random instead of being essentially fixed and like predetermined in this case. But it turns out you can use a similar like influence score based approximation even with those additional changes. And then the big question becomes, and I think, so we have actually a separate discussion paper where the discussion paper is on one topic, but we talk about this in our discussion and response. Then all of these cases, the bootstrap in this case and so on, the question isn't so much, can I form this approximation? That's really simple. It's just this first order Taylor approximation. There's nothing crazy going on there. It's, is it any good? And so that becomes the real question with the bootstrap approximation, much like in this one, is like, is this approximation any good? And we find in the bootstrap case, unlike this case, that the first order Taylor series approximation, you kind of don't expect to be good enough in this like comparison sense that I was sort of getting at with the theory here, like for what it means good enough. And that you actually have to do something like a second order Taylor series approximation or a higher order one to get somewhere with that. And I think that's just because of that wider range of W values and bigger change you can see in the W values. Here we're really constrained to have that small alpha fraction, if that makes sense. Cool, thanks.
A really great talk, Tamara. I have a question that I guess is a little bit building on the question Ronan just asked, which is, I'm like really stuck on your slide number 5, which was the same one that was asked about here, where there's the example with 15,000 data points. And if you take out 15, then I don't remember, the effect appears or disappears or switches sign or whatever. And the thing that I am stuck on is somehow it doesn't feel terribly surprising to me that if you have 16,560 data points and you're allowed to choose like an adversarial 15, like 16,000 choose 15 is like 10 to the 60 or something crazy, like a lot more than even the exponential number you showed earlier. And so I guess I wouldn't necessarily be so surprised. I guess I'm saying it wouldn't make me doubt an analysis that if I chose an adversarial 15 that I could change the effect. By contrast, if you bootstrapped and you did like 10,000 bootstrap data sets and only, a third of them showed that effect, then that would make me really worried.
Yeah, so let me put it this way. I think there are 2 ways to think about this. So one is we find in talking to practitioners that this is easier for them to wrap their heads around than something like a KL distance or something like that. But that being said, we should still think, is this really a meaningful thing? So
would you be stressed? Like, would you be, I'm asking sort of like, would you feel stressed about publishing a result that was non-robust in this way? Because I guess I'm not sure
think of that as being the meaningful. So let me use meaningful as meaning that. So 2 things. So one is, let's suppose that I was in the situation I originally described, where I'm comparing people who received microcredit and people who did not receive microcredit. So in this case, if it were truly the case that, let's say, basically everybody has a matched person who had the exact same business profit as somebody in the other arm, and there were just 2 people who had way more business profit. This is something where a randomized procedure is not likely to pick up this 1 or 2 people, but a worst case procedure would. And so we would want a worst case procedure to flag that. I think another perspective on this question is, in fact, the signal-to-noise interpretation. So that this is picking up a signal-to-noise in the data analysis, and that that's a useful thing to know about. And so from this perspective of, hey, do I have enough signal in my analysis to know what's going on? And I would say in this particular paper, there's two types of data analyses that we really saw. So one was the one I just described. Like if you actually look at some of this data, it really does look like what I just described. There's just a few data points that are out there. But again, it's not just outliers. So what we saw, for instance, in the example that I gave with simulations, but also I find in a lot of real life analyses, is you truly just have a blob. And you'll have practitioners sort of saying, oh, wow, yes, my sports supplement really has a major effect on my marathon performance in running. And you can see that I have this very small p-value, and you look at the actual values, and it's truly just a blob. And this is flagging that. It's flagging that you have these corners, these issues. I think the third thing that from an intuitional perspective is this p-hacking example, that you actually can set up a p-hacking analysis, which this Michael guy did, and then see, hey, this is flagging the p-hacking. And so even if you don't buy, like, man, I'm worried about, like, hey, this super tiny fraction dropped in and of itself, although I do think that's intuitive for many people, you can think about these illustrative examples that I think really are showing, hey, these are cases where I would care about it, and the random perspective isn't going to pick that up on its own. Thanks. Yeah?
Can I suggest, because we're 5 minutes over, we move the rest of questions offline?
Yeah, super happy to keep chatting.
Okay, so let's thank Tamara again.
Thank you so much.